Everything turns on a charge roughly $2. Once you follow it through the GPU, the real systems trade-off comes into focus. The industry assumes that renting artificial intelligence infrastructure is a pure software transaction. We treat it as a simple matter of spinning up an instance and running code. But that $2 hourly rate obscures the fact that a standard 8 GPU server requires over 10 kilowatts of power, shifting the math from compute to cooling. The true cost of the H100 GPU providing baseline hardware isn't the silicon. It is the massive facility and networking tax required just to keep it fed. This is no tech. Open any major cloud pricing calculator today, and the proposition looks incredibly simple. Take a specialized AI cloud provider's H100 instances, for example. You select the hardware tier, you provision the node, and a tiny meter starts running. This is the $2 ticker. It represents the deceptive simplicity of cloud operating expenses. When an enterprise can rent AI infrastructure for roughly $2 an hour, the capital expenditure of buying physical hardware seems completely irrational. After all, the NVIDIA H100 SXM 80 GBB GPU typically commands a capital expenditure of $25,000 to $40,000 per unit. Meanwhile, specialized cloud providers charge roughly $2 to $4 per GPU hour for on-demand access to equivalent instances, while hyperscalers command closer to $12 to $15. The common belief is that the GPU is mainly about the headline mission profile. We assume we are paying for raw processing power, and if raw compute was the only variable that mattered, the $2 hourly rental would be the most efficient financial model in the history of enterprise technology. You would never need to buy a physical server again. But the deeper story sits inside that charge, roughly $2, and the physical trade-offs it forces. The cloud interface abstracts away the physical footprint, presenting an illusion of frictionless capacity. Because when you move from a single cloud instance to a production-scale deployment, the bottleneck shifts entirely away from the processor's ability to do math, which introduces a structural problem. If we are primarily buying these $40,000 chips just to pool their 80 gigabytes of memory, what happens when the network connecting them becomes the actual bottleneck? We will trace that exact breaking point in the networking rack later. First, we need to look at what happens inside the silicon itself. Now move from the cloud pricing calculator to the actual hardware architecture. Look closely at the layout of this board. The central processing cores are surrounded by high-bandwidth memory modules. The physical distance between the compute cores and the memory is measured in millimeters, but in operational terms, it is a massive gulf. When an enterprise runs a large language model, they are not usually constrained by how fast the chip can calculate. They are constrained by how much data they can hold in memory at one time, and how fast they can move it to the cores. The H100 has a memory bandwidth of 3.35 terabytes per second. At first, that sounds like a limitless ceiling. But for modern AI inference, it is a suffocating bottleneck. Despite offering up to 3,958 T-flops of FP8 compute, the H100 is frequently memory capacity and memory bandwidth bound for LLM inference. To understand why, look at the operational math. A 70 billion parameter model running in 16-bit precision requires roughly 140 gigabytes of memory just to load the weights. That is before you even account for the key value cache required to process user prompts and maintain context during a conversation. Every single user query demands its own dedicated slice of memory. If you have 10,000 concurrent users, that cache requirement balloons instantly, eating into whatever VRAM you have left. Because the model weights are so massive, a single 80 gigabyte chip cannot hold the entire model in its memory. This forces a brutal architectural compromise. Enterprises are forced to provision expensive multi-GPU nodes primarily to pool VRAM rather than for raw processing power. This is the reality of pooling VRAM. You are not scaling out because you need more math. You are scaling out because you need a bigger bucket to hold the data.
The HGX H100 baseboard schematic isn't just a layout. It is a physical admission that a single chip cannot survive modern AI workloads alone. And once you put 8 of these chips into a single metal box to share that memory, you trigger a chain reaction that breaks traditional data center design. Step off the architecture diagram and walk onto the data center floor. This is where the financial abstraction of the cloud calculator collides with the laws of thermodynamics. The thermal design power, or TDP, of a single H100 SXM5 is 700 watts. When you pack 8 of them together, the math becomes unforgiving. A standard 8 GPU server requires over 10 kilowatts of power just to operate. 10 kilowatts in a single rack unit is not a normal IT deployment. We actually broke down how these constraints dictate build versus rent decisions in our episode, Why the Story of the Economics of GPU Compute Gets Simplified. That one goes deeper into how memory bandwidth and power consumption, not raw speed, force organizations to over-provision hardware, and it is worth a watch if you want the full silicon breakdown. But here, we need to follow that heat out of the silicon and into the facility itself. Traditional data centers were built to cool racks that draw maybe 5 to 8 kilowatts for the entire cabinet. Now, a single server demands more cooling capacity than an entire row of legacy hardware. This is the 10-kilowatt thermal wall. Air has a terrible volumetric heat capacity. You can blow hurricane-force winds through a server chassis, and it still will not strip heat away fast enough to keep a 700-watt piece of silicon from melting. The fans would have to spin so fast they would physically shatter from the vibration. So the facility is forced to plumb water directly to the processors. These D2C liquid cooling manifolds are not optional accessories. They are mandatory infrastructure. You are no longer just managing data, you are managing industrial fluid dynamics. This makes electricity and specialized liquid cooling infrastructure a dominating factor in long-term total cost of ownership. Because the moment water touches the server rack, the financial models used to justify buying hardware begin to fracture. Open the internal procurement documents of any enterprise trying to build their own AI cluster. The standard industry math claims that if you run a workload continuously, buying hardware becomes cheaper than renting it. The theoretical break-even point for renting cloud GPUs versus purchasing on-premise H100 infrastructure is often modeled at 12 to 18 months of continuous use. At first glance, this justifies massive capital expenditures. But that timeline is a fiction. It assumes you are only buying the computers. When financial teams scrape public cloud documentation to build these TCO models, the numbers often break. You will frequently spot internal dashboards throwing errors, notes that an LLM JSON parse fallback was used, built from available source snippets and summaries. And even when the calculators function, critical variables, baseline metrics for power usage effectiveness, or PUE, and cooling overhead are simply omitted. This happens because vendors deliberately obscure the true facility costs behind clean pricing tiers, leaving procurement teams to guess at the actual physical overhead. The reality is that retrofitting a legacy data center to support those D2C liquid cooling manifolds and 10-kilowatt power densities requires tearing up the floor. It means reinforcing the structural steel to handle the sheer physical weight of the coolant loops. It requires new substations, new backup generators, and reinforced concrete just to hold the physical weight of the coolant. Hidden costs like data center retrofitting, InfiniBand hardware and fabric management, and data egress often make a conservative estimate for true break-even closer to 36 months. And that data egress penalty is severe. Moving petabytes of training data out of a cloud provider and into a physical facility triggers massive network fees before a single model is trained. But even if an enterprise can afford the plumbing, the power, and the 36-month wait, they hit the final hidden constraint. Remember that delayed question we asked earlier? Back to the screen we opened in Chapter 1, the HGX H100 baseboard schematic.
If we are primarily buying these $40,000 chips just to pool their 80 gigabytes of memory, what happens when the network connecting them becomes the actual bottleneck? This is where the architecture finally breaks the budget. Step into the back-end networking aisle. When you provision an instance in the cloud, the provider has already solved the networking problem for you. But when you build it yourself, you discover that standard Ethernet cannot handle the bandwidth required to keep these GPUs fed. The protocol overhead is too high, and the latency spikes cause the processors to stall. You have to build a parallel, dedicated network just for the GPUs to talk to each other. This requires Remote Direct Memory Access, or RDMA. It allows one GPU to read another's memory across the room without bothering the central processor, bypassing the operating system entirely to keep the data flowing at line rate. In massive AI training clusters, back-end networking infrastructure, including InfiniBand switches, 800G optical transceivers, and specialized cabling, can consume 15 to 20% of the total hardware capital expenditure. It completely disproves the misconception that GPUs are the only significant infrastructure cost. You are paying a massive premium just to let the chips share their memory pools at scale. The network becomes a tax on the memory pool. If you under-provision the network, your $40,000 GPUs sit idle, waiting for data. If you over-provision it, your capital expenditure spirals out of control. You aren't buying compute, you're financing a liquid-cooled memory pool. Everything turns on that initial promise. The illusion of cheap compute shatters when you realize a standard 8-GPU server requires over 10 kilowatts of power, shifting the real NVIDIA bottleneck from FP8 operations to facility-level cooling and VRAM pooling. But the 8-GPU server opens a harder question. What would it take to replace it without raising the failure budget? No. Tech documents the hard physical constraints underlying abstract cloud economics. When you look at the 8-GPU server, which constraint matters most? Processor choice, failure budget, or replacement cost? See you in the next thermal footprint.